Hello, Physics C students. Today we're going to talk about capacitors and dielectrics and what happens when you put a dielectric into a capacitor. How would a dielectric affect things like overall capacitance, the charge density, the electric field, the voltage between the plates in various situations where capacitors are hooked up to voltage sources, plate separations changed, dielectrics in, dielectrics out, in all kinds of different combinations. That'll kind of wrap things up, but first we should define what a dielectric is and go over the very basics of what happens to a dielectric when it's exposed to an external electric field. So a dielectric is just another word for an insulator. That could be almost any non-metal material, so a non-conductor. And normally the atoms in a dielectric are kind of randomly arranged. You can see an example of that right here. Right, it's a capacitor, an uncharged capacitor with a dielectric between the plates of the capacitor, and the molecules here are all kind of like randomly arranged so that each little tiny electric field they have. And they do have little tiny electric fields, right? So the electric fields point from plus to minus. So each one of these little atoms here has a little tiny electric field pointing from plus to minus. But because they're all kind of like randomly arranged, if you were to add up all those little tiny vectors, you would get a total vector that is basically zero. Right? It has no length to it, no direction, so zero magnitude on average. But when you put a dielectric into an electric field, these little molecules can kind of rotate themselves to a slight degree, or the electron clouds can shift a little bit to spend more time on one side of the molecule than the other. And all of these little tiny electric effects, when you add them up over all of the molecules in a dielectric, which would be a lot of them, can produce a very noticeable effect. Let's take a closer look at an example of a dipolar molecule, a polarized molecule, and you'll understand a little bit more about why this happens. So here we have a water molecule. We've got the two hydrogens on the bottom, right? Two hydrogens on the bottom and the oxygen up here, and the electrons from the hydrogen atom want to spend more time on the oxygen side than they do out here, right? They share electrons, so they're going to be over here more often. And so what effect does that have? It leaves this bottom side of the atom, from this perspective, more of a net positive charge, and it leaves the top side of the atom with more of a net negative charge. And so this acts like a polarized molecule. We call it a dipole. And you can see how this would respond to an electric field, because this is essentially positive charges at the bottom, negative charges at the top, and we know that charged particles will experience an electric force. So when we put a charge on our capacitor, when we put a charge here, we're going to get the electric field from the plates pointing down. Oops. This would be the original electric field from the plates pointing down. We're going to have the little tiny electric fields from the slightly rotated molecules pointing up in opposition to the downward field from the plates. And in total, this is going to give us a net electric field which points downwards. The electric field from the dielectric cancels out the electric field from the plates just a little bit. And that's what we have here. The net electric field is the electric field of the plates minus the electric field of dielectric. One way that we can measure how polarized, or how much of an induced kind of rotation takes place within a dielectric, is by a factor called kappa. And on the Physics C equation sheet for this year, you have an equation which says that kappa equals epsilon over epsilon naught. And we could rearrange that to get epsilon equals k epsilon naught. Now, this hasn't been on the equation sheet previously, I don't believe. And because it's new this year, I can't say how important this will be on the Physics C test, but I can't imagine that it's going to be very prominent. And you should be careful because epsilon is going to be used in several different contexts in this course. We have epsilon naught already, which is the permittivity of free space or a vacuum. We now have this epsilon, which is a permittivity of the dielectric. And we'll also have epsilon used in circuits coming up, which is going to be for a voltage source or an electromotive force. So there's 3 different times and situations in which epsilon is used. So just be careful with epsilon and be aware of the context of the problem. Epsilon naught is the vacuum permittivity, which is a measure of how electric fields pass through empty space. Epsilon is the permittivity of the dielectric, which is a measure of how the electric field kind of passes through the dielectric. And we looked at this relationship here saying epsilon equals k epsilon naught. Basically, the value of kappa, as kappa gets larger, it increases the polarization effect within a dielectric. They become more and more easily polarized. Now I've got a picture of a capacitor over on the right. This is kind of like a side view of this one on the left. There's usually no gaps here at the top and the bottom. They're here just so we can distinguish between the metal slab that's in the middle and the plates. This is going to have some positive charge density on it, plus sigma. This would have some negative charge density on it, minus sigma. And the dielectric in the middle is going to, when those molecules twist, we're going to get some like surface charge density on there. So this would have an induced charge density, and that would be plus sigma, and this one would have an induced charge density of minus sigma. Our net electric field is going to point from the positive plate down towards the negative plate. I'm going to try to draw my lines roughly parallel, because in a parallel plate capacitor we have a uniform electric field. This is the net electric field that's on the inside of the plates. That means it's the field from the plates minus the induced field of the dielectric. And if I apply Gauss's law here, we get E equals sigma over epsilon. And I'm going to use epsilon because of the dielectric. Well, if we substitute in here that epsilon is k epsilon naught, we'll end up with sigma over k epsilon naught for our electric field between the plates in magnitude. Just so you get a little bit of an idea of what this factor of K is kind of telling us, I got a chart here that I'll share with you. And in this chart, we can see the dielectric constants. We can see that air is almost the same as a vacuum. And we can see some things have relatively small dielectric constants, like paper, 3.7. I've seen values for paper that range between 2 and 4. We just finished up a lab where you found the dielectric constant of paper by making a capacitor out of aluminum sheets and changing the number of pages between it in a textbook. And I know some of you got values close to this. If you got something way off from this, come and see me. We should go over why, or you should definitely figure out why that didn't work out correctly. We see some things with very high dielectric constants, 233 for strontium titanate. And then there's also this breakdown strength column on the right, which tells us at what voltage would these insulators start actually like conducting electricity and break down. We use the breakdown voltage of air, 3 times 10 to the 6 volts per meter. We use that in the lab where we calculated the charge on the Van de Graaff dome. Remember, we measured the length of the spark, and we used this value to calculate the voltage that would be on the dome. So when you're constructing a capacitor, designing one, you want to be aware of both the dielectric constant and the breakdown voltage, because if you designed a capacitor and then you put too much voltage on it, you could actually cause breakdown between the plates. Let's go back to here. So we just looked at some values there, and let's go over what those mean. We said K for a vacuum was equal to K of air, which was equal to 1. And that's going to give us the electric field equals sigma over 1 times epsilon naught, which is just sigma over epsilon naught. Excuse me for 1 second. And K for a dielectric is greater than 1. So we get E equals sigma over K epsilon naught. We could also say here that sigma is Q over A. This could also be Q over K A epsilon naught. And for a conductor, K is basically going to be infinitely big, which means our electric field would be divided by infinity. And we know that when we divide by infinity, we get a net electric field of 0. And this should make sense because in a conductor, if we put a conductor in the middle here, if it was touching these plates, the charges could flow and the capacitor would just essentially discharge itself, and then there'd be no electric field. Even if this slab wasn't necessarily touching the conductor, this charge density would be equal to this charge density. And so if you had if you were measuring like the electric field in the middle, it would still be 0 because we know there's no electric field inside of a conductor when it's at equilibrium. So the greater the value of kappa, the larger this charge density that's induced becomes. Okay, let's take a look at the next page. We're going to look over this chart. I'll show you some resources that you can use, and that'll wrap things up for the day. When a capacitor is connected to a voltage source, the voltage is going to be constant. That's why it's called a voltage source. and the amount of charge can change. So the voltage source is going to do whatever it needs to do in order to keep whatever it's connected to at 20 volts. It's going to try its best. It's going to pump out more charge if it's needed. It's going to kind of take charge back if it needs, but whatever, it's going to try its best to keep that voltage difference between one side and the other constant. So charge can flow off. It has a wire by which charge can flow off, but the voltage is going to be constant when it's connected to the source. If you disconnect the capacitor from the voltage source, the charge is going to be fixed because now you've disconnected the wire. There's nowhere for the charge to go, no escape. So the charge is fixed, conservation of charge, right? It's not created or destroyed, it's going to stay there. And the voltage can change in this situation. How would the voltage change? Voltage might change when you put a dielectric in, take the dielectric out, change the plate separation. If you could change the plate area, the voltage would change, things like that. Remember, there's a variable capacitor with a little knob and overlapping plates. So in this chart that we're going to look at, you only need to tell me by what factor these things change. Like, does it go up or down by a factor of kappa? Or here we see that this changes by a factor of 10. So does the electric field or voltage increase or decrease by a factor of 10, say? Right here it's changing by a factor of 2. So does it change by a factor of 2? If you have a dielectric, it's going to change things by a factor of kappa. Or you could say that they're constant. Okay? So that's a little bit about the chart. The first 4 are all charged and connected. Or sorry, charged and disconnected. And we know that when it's disconnected, the charge here is not going to flow on or off, right? That's going to be constant. If we leave it connected, then the charge can change, but the voltage here would be constant. So again, disconnected means the charge stays the same, but the voltage here could change. When it's connected, the charge can change, but the voltage would stay the same. And there's some equations that you can use to help yourself with this chart. We said from the previous page that E was equal to sigma over K epsilon naught. And we know that sigma was the charge density, which was Q over A. So that's going to be one equation that might be useful for this chart. We also know that E equals delta V times D for a constant field, which between the plates of a parallel plate capacitor, we do have a constant electric field. If I substitute that in, I'll get equation number 2. Delta V times D equals Q over K A epsilon naught. Equation number 3 is just going to be the definition of capacitance. C equals Q over delta V. But remember, capacitance is a property of the physical characteristics of the capacitor, the dimensions. And spherical, cylindrical, and parallel plate capacitors all behave a little different. But for parallel plate capacitors, we know the capacitance is K epsilon naught A over D. And if I combine equations 3 and 4, I will get equation 5, which is going to give me Q over delta V equals K epsilon naught area over distance between the plates. With those 5 equations, you should, and the simulation and the other resource I'll show you, you should be able to complete this chart. One of the resources you can use is a great Walter Lewin video that I'll link on Canvas. Walter Lewin was an MIT professor for many years, and he does a great job demonstrating some of these in his lab setup there at MIT. That's a good thing to watch. He has all kinds of meters, and you can see the charges flow on and off as he's changing the plate separation and stuff. And there's certainly something to seeing it happen in reality versus watching a simulation. Speaking of simulations, there's also a simulation to help you with this chart. I think in the video, Walter Lewin covers the first 4 examples here, maybe. And in the simulation that I'll show you, which is here, this is courtesy of Dan Hosey, another physics AP physics teacher. Thank you, Dan, for sharing this. If this is open, you don't need this to be open. There's nothing here that you need to change. But what you can do here is change the battery. We could change the area of the plates, but we're not going to do that. You can change the plate separation. You can see the capacitance, the electric field. You can change kappa. You can view this in 2 different ways. I prefer to see the actual value, so I don't have it in terms of epsilon naught. And just for an example, K equals 1, that means no dielectric. So here, I'll charge the capacitor up to 500. I will start off with a small plate separation. So it's charged with a 1 meter separation. I'll disconnect it from the battery. And now I can change this to be 10. Right, so I increased the separation by a factor of 10. What happens to some of these other quantities? I could also do something like have it charged up, and now I could insert a dielectric and see what happens. So there you go. Check Canvas. There'll be a link to the Walter Lewin video and a link to this simulation here. Thank you for your time. I appreciate it, and I look forward to seeing you soon in class. Yabba dabba doo.